All right, let's just dive right into this high-stakes exam roadmap covering multiplexing, modulation, and spectrum management. I'm going to be your tutor for this explainer, and my only goal today is to fast-track your prep. We're cutting out all the fluff. We are focusing strictly on the high-yield formulas, the critical mechanisms, and most importantly, those notorious trip-up zones that literally cost students points on competitive exams. If you've ever found yourself kind of confusing the pure math of signal processing with the pure rote memorization of spectrum regulations, well, you're absolutely in the right place. Here's our syllabus for today. We're going to cover 5 critical modules: multiplexing fundamentals, TDM math and configurations, code division multiplexing, delta and pulse modulation, and finally RF spectrum management. Just a quick heads up, the biggest trap here is skipping straight to the math without nailing the basic definitions first, so we're definitely not going to make that mistake. Section 1. Multiplexing Fundamentals. These are the foundational rules for sharing a single communication medium. Let's see how this sets the stage for everything else. Okay, we really have to lock in this strict definition before we hit the heavy math. Basically, multiplexing is just the process of combining several independent signals into one composite signal, so you can send it over a single medium. Now, you already know there's a multiplexer on the transmitter side, right? But the classic exam trap? Forgetting the demultiplexer at the receiver side. That demux is absolutely mandatory if you want to separate that composite signal back into its original independent parts. So the whole multiplexing landscape essentially breaks down into 4 main players, and you've got to have these memorized. First up is frequency division multiplexing, or FDM, which assigns different frequency bands. Think radio broadcasting. Next is time division multiplexing, TDM, which uses different time slots, super important for digital telephony. Then we've got wavelength division multiplexing, WDM, which relies on different wavelengths. And finally, code division multiplexing, CDM, which separates signals using unique codes. Now, the massive trip up here, it's application mapping. If a test question asks which technique is used in optical fiber communication, lock in WDM immediately. Seriously, do not second guess it. Moving on to Section 2, TDM math and configurations. This is where multiple digital signals are transmitted sequentially using rotating commutators. All right, shifting gears into TDM, this is exactly where your math skills are going to be put to the test. The most crucial thing with TDM is calculating the total bit rate perfectly, and that means keeping an eye out for a hidden trap. The basic bit rate, R sub b, is just n, the number of bits per sample, times n, the number of channels, times f sub s, the sampling frequency. Simple enough, right? But here is where exams get super sneaky. TDM relies on a commutator at the transmitter and a decommutator at the receiver, and they have to be perfectly synced up. To make that happen, an extra sync bit, which we call A, is often added. If a problem even mentions an extra bit for synchronization, you have to use the modified formula. R sub b equals n times n plus a, all multiplied by f sub s. Let's actually run a rapid-fire drill on this exact formula to see how we get to 1280 kilobits per second. Say the problem gives us a TDM link with 20 channels, so n is 20. Each is sampled 8,000 times a second, making f sub s 8,000. Each sample has 7 bits, so n is 7, and it mentions an additional sync bit, meaning a equals 1. Now, the fatal error students make is multiplying n, and f sub s, and then just tacking on a 1 at the very end. No, you have to add that sync bit a to n first. So it's n, which is 20, times f sub s, 8,000, times the total bits per frame, which is 7 plus 1. That gives us 20 times 8,000 times 8, which is 1,280,000 bits per second, or 1,280 kilobits. The math on this is absolute. I love this comparison because it perfectly illustrates the core difference in how we stop signal collisions in the analog versus digital worlds. On the FDM side, we rely on frequency guard bands, represented by G. To get the total FDM bandwidth, it's the number of channels times the bandwidth of each, plus the guard bands in between. And FDM uses bandpass filters to separate everything out. But then, look at TDM. It doesn't use guard bands at all. Instead, it relies on strict timing synchronization and low-pass filters to stop aliasing. Do not mix these two up on test day. Guard bands are always FDM, synchronization bits are always TDM. All right, Section 3, Code Division Multiplexing, or CDM, where users share the exact same time and frequency, separated only by unique orthogonal codes. This one kind of defies the physical rules we just talked about. What's genuinely fascinating about CDMA is how it mathematically turns every other user's signal into just background noise. Unlike FDM or TDM, CDMA users are on the exact same frequency band at the exact same time. How does that work? Spread spectrum technology. Step 1. Every user is assigned a unique orthogonal code, like a Walsh, PN, or Gold code. Step 2. Your message is multiplied by this code at the transmitter. Step 3, at the receiver, that composite signal gets multiplied by the exact same code again. Because the codes are mathematically orthogonal, your specific message pops out perfectly in step 4, while everybody else's transmission just registers as low-level static. It's a brilliant way to get massive security and noise immunity. Moving to section 4, delta and pulse modulation. This is all about encoding analog signals into digital formats with varying bit efficiencies. Bandwidth efficiency is a huge exam topic here. The hierarchy here is absolutely critical. PCM demands the most bandwidth, while delta modulation is fiercely efficient. Let's track the evolution. Pulse code modulation, PCM, encodes the absolute value of every single sample using n bits. Differential PCM, DPCM, uses a prediction filter to only encode the difference between consecutive samples, which obviously takes fewer bits. But delta modulation, or DM, takes the crown. It uses a 1-bit quantizer. Literally, it just asks, did the signal go up or down? Since n is just 1 in delta modulation, its bandwidth requirement is merely f sub s divided by 2. If an exam question asks for the lowest bandwidth requirement, your answer should instantly be delta modulation. Now, because delta modulation only uses that 1 bit, it relies on a fixed step size, which we call delta, and that leads to 2 heavily tested distortions. First, if the original signal changes way too fast for the step size to keep up, you get a slope overload error. The math condition there is delta is less than delta optimum. The fix, you gotta increase the step size. On the flip side, if the signal changes too slowly and your step size is too big, you get this blocky distortion called granular error, meaning delta is greater than delta optimum. The fix for that is to decrease the step size. Whatever you do not invert these fixes on the test. To perfectly track a signal and avoid those distortions, we need the optimum step size, or delta opt. Basically, the derivative of the message signal has to equal delta opt divided by the sampling time, t sub s. When you run the calculus on a standard sine wave, the max slope gives us this golden formula. Delta opt equals 2 pi times the signal frequency times the amplitude times the sampling time. Now listen closely, because here is the classic trick. The exam is probably going to give you the sampling frequency, f sub s, not the sampling time, t sub s. You have to consciously remember that t sub s is equal to 1 over f sub s and swap that into the equation. Let's actually work through a live exam question to see how this formula spits out exactly 6.28 volts. We're given an amplitude of 4 volts, a signal frequency of 1 kilohertz, and a sampling frequency of 4,000 samples per sec. Setting it up, we rearrange things so delta opt times f sub s equals amplitude times 2 pi times the signal frequency. Plug it all in. Delta opt times 4,000 equals 4 times 2 pi times 1,000. Boom, the 4,000s on both sides cancel out immediately, leaving delta opt equal to just 2 pi. Since pi is 3.14, your optimum step size is 6.28 volts. A ton of students forget that 2 pi multiplier from the derivative step and incorrectly bubble in 1 volt. Don't be that student. Final section, section 5, RF spectrum management. We're regulating the finite 3 kilohertz to 300 gigahertz natural resource. We're in the final stretch now, transitioning from pure math to pure memorization. You absolutely have to memorize these frequency bands. It is practically a guaranteed point on your test. The RF spectrum is a finite resource, capped essentially from 3 kilohertz to 300 gigahertz, and it's sliced up very strictly. Notice that AM broadcasting is way down in the lower frequencies, from 300 kilohertz to 3 megahertz. But FM radio and TV jump way up into the 30 to 300 megahertz range. Mixing up the AM and FM bands is literally the most common mistake here. Moving higher from 300 megahertz to 3 gigahertz, you've got the super crowded mobile communication bands, hello 4G and 5G. And above that, satellite communication from 3 to 30 gigahertz. Seriously, take a mental picture of this slide right now. Because the spectrum is so finite, it needs intense regulation. Globally, the International Telecommunication Union, the ITU, manages this. If you happen to be taking a regional exam in India, the specific allocation body is the Wireless Planning and Coordination Wing, or WPC. A massive trap here is selecting TRI, which is the telecom regulator, when a question specifically asks about spectrum allocation. The correct technical answer is WPC. They're the ones managing auctions and enforcing interference control using strict filtering, power control, and yep, our old friends, guard bands. Okay, let's nail this final drill question about guard bands just to lock it all in. A very common test question will ask, guard bands are used in spectrum management to do what? The absolutely correct answer is reduce interference. They're literal physical buffer zones. The distractor options will try to trick you by claiming guard bands increase bandwidth or increase power. Totally false. Guard bands actually waste a chunk of usable bandwidth to act as a wall between adjacent FDM channels, intentionally sacrificing raw capacity just to keep the signal integrity intact. As we wrap up this explainer, I want you to ask yourself a question. With the spectrum being rigidly finite, capped effectively at 300 gigahertz for these uses, how is your generation of engineers going to break the rules? We've just conquered the strict math of TDM, the frequency guardrails of FDM, the mathematical sorcery of CDM, and the sheer efficiency of delta modulation. But physics says we can't just spawn more spectrum. We have to get infinitely more efficient at using what we already have. Are you going to be the one to design the next multiplexing protocol that shatters these limits? Review this material, master these formulas, and go absolutely crush your exam.